as the question says, a small spherical ball is released from a point at a height h on rough track shown in figure. Assuming that it does not slip anywhere, find its linear speed when it rolls on the horizontal part of the track. Now we can say that it is having some potential energy over here. It will roll down to the bottom of this track and will be having some kinetic energy, that is linear kinetic energy due to its velocity v, while it will also be having some rotational energy due to its rotation, that is omega. Now we can easily do the energy conservation for this problem, in which we can write down the initial energy being mgh because it is at a height of h, being converted into rotational kinetic energy, that is half I omega square, and the linear kinetic energy, that is half mv square. Now, there may be a question in your mind that why we haven't considered the loss due to the friction, because they have given us the rough track. The point is that they have also given us that it is not slipping anywhere. That is, when this ball is actually rotating, then this point of this sphere actually comes at rest with respect to this surface, which means that if it is not slipping, then the friction acting is zero, because there is no relative motion between the sphere and the surface, and friction acts only when there is some relative motion. And since they have also given us that it is not slipping, which means that losses due to the friction are zero over here. That is why we haven't added any losses, right? That's why you could conserve energy. If they won't have given it slipping, that if the ball could slip, then you couldn't apply the energy conservation. Now, putting the values over here, we get 9h equals to v square by 5 plus v square by 2, giving us a velocity of under root 10 gh by 7.